Hey you guys, in this section we are going to cover trigonometric equations and inequalities part 1. Okay, so if you guys remember earlier in this chapter we talked a lot about identities. Okay, and identities, if you guys remember, for example, one of the ones we covered was the Pythagorean identity, which says cosine squared theta plus sine squared theta equals 1. Remember, this was considered an identity because the left-hand side and the right-hand side were equivalent. Anytime you saw this, you could replace it with 1. Anytime you saw 1, you could replace it with the left-hand side. They were equivalent. Those were identities, okay? Now, in this section, what we're going to start looking at are conditional equations, okay? Conditional equations are only true for specific values, so they're not always true. So an example of a conditional statement are the equations that you're used to. So if we go back to college algebra, if we were to have something like x plus y equals, let's erase the y, x plus 8 equals 10, okay? If we were to solve that equation for x, we would subtract 8 from both sides, and x would equal 2. This is an example of a conditional equation because this is only true when x equals 2. If you plug anything else for x into this equation, it's not true. So it's conditional. It's only true under certain conditions. Okay, so that's what we're going to look at in this section, except we're going to apply it to trig world. Okay, now the important thing is when you are solving these equations that I'm about to give you, okay, everything that you used to do in college algebra is fair game here. All right, so there's going to be a couple of steps that you're going to walk yourself through when you're solving these equations analytically. Okay, so step 1, the first thing you're going to do is you're going to decide whether your equation is linear or quadratic so that you can determine the type of solution method you're going to use. Okay, so remember, anytime you have a linear equation, okay, the highest degree that you're going to see is 1. Okay, anything that's quadratic, the highest degree you're going to see is 2. Okay, so that's what you're going to be looking for, are the exponents, to determine whether or not the equation you've been given is linear or if it's quadratic. Okay. Step 2, the next thing you're going to see is to see how many trig functions do you see presently in the equation that you've been given. Okay, so you want to count them. Do you have cosine and sine? Do you only have tangent? Do you only have cosecant? You need to figure out how many trig functions you have. Okay. Step 3 says, okay, if you have more than one trigonometric function, rearrange the equation so that one side equals 0, and then you're going to try to factor and set each factor equal to 0 to solve. Okay, so you're going to do that if you have more than one trig function there. Okay. Step 4 says, if the equation is quadratic in form, which means it looks something like a quadratic, right? It looks something like ax squared plus bx plus c equals 0. It resembles something like that, which is quadratic in form, but it's not factorable, okay, which means that you can't factor it. You're going to use the quadratic formula, and then you're going to check your solutions to make sure that they're in your desired interval, okay? And then step 5 says, you're going to try to use identities to change the form of the equation. It may be helpful to square each side of the equation first. If this is done, you're going to check for any extraneous solutions. So extraneous values are the ones that you got when you solve them, but when you plug them in, they don't make your equation true. Okay, so as you are solving each one of these problems, you're going to walk yourself through these steps to figure out if your problem falls into any one of these categories, and then you're going to proceed farther. All right, so let's look at the first example that we've been given. So the first example says directions, solve 2 sine x minus 1 equals 0. And they want us to solve it for part A over the interval from 0 to 2 pi, and then for B for all the solutions. Okay, so the first thing I'm going to do is write our problem out. All right, so our step said the first thing we needed to determine whether our function is linear or quadratic. Okay, so as you're looking at this problem, do you see any degrees that are higher than 1? Nope. This sine function is raised to the first power, so we can already determine that this function is linear. Okay, so that's the first thing. So we're going to treat it as if we're solving a linear equation. It just has a trig function in it. The second thing they told us to determine was how many trig functions are present. So the only trig function I see here is sine. There's nothing else there. There's no tangent, no cotangent, none of our other 5 trig functions. So I'm good to go. I can go ahead and solve this for sine x. So my goal is to isolate that by itself. So the same way that you would isolate x in just an algebraic equation, same thing you're going to do here. So the first thing I'm going to do, I'm going to move this 1. So it's subtracted here. So in order for me to move it to the other side, I need to add it. All right. Then I need sine x to be by itself. So there's a 2 out in front and the 2 is being multiplied. So I'm going to divide both sides by 2. So that's going to give me sine x equals 1/2. Okay. And remember, your goal is to get x by itself. But right now, that x is embedded inside of that trig function. So if you guys remember, the only way we can get the x out is that we have to inverse it. Okay. So we need to write x is equal to inverse sine of 1/2. Okay. So when we're answering an inverse trig problem, remember your answer is an angle. So this question is asking me for which x values or for which angles does sine equal 1/2, okay? And they already told us up here that we are interested in the interval from 0 to 2 pi, okay? So what I've done is I've brought over our unit circle. All right, and we are interested in this. X equals sine inverse of 1/2. So we are interested on which angles on this unit circle have a sine value of 1/2. So let me change our color. Okay, so our sine value, remember, is our y value. So as I'm looking at this unit circle from 0 to 2 pi, I'm looking at the angles that have a y value of 1/2. All right, so let's look at that. So we know that sine is positive in the first and second quadrants, okay? So pi over 6, its y value is 1/2, okay? And if I look over in the second quadrant, 5 pi over 6 has a sine value that's 1/2. So those are my only 2 angles within the interval from 0 to 2 pi that have this particular sine value of 1/2. So I can go ahead and write that in for my answer. So I'm going to go back over here. Okay. All right. So when you go to write your answer, you may be wondering, well, do I write it in degrees or do I write it in radians? Pay attention to your interval. Okay. Whatever your interval is written in is what your answer needs to be written in. So right now my interval is from 0 to 2 pi, which is in radians. So automatically they're going to assume that they want my answer in radians as well. So we just found that x equals pi over 6 and x equals 5 pi over 6, okay? Those are going to be my 2 answers for A. All right, so then let's go look at B, okay? So B wants to know, all right, they wanted us to solve this equation, but they want to know all the solutions that exist. So not just the ones that fall in the interval between 0 and 2 pi. So if they're interested in all the solutions, okay, we already found the 2 that fall between 0 and 2 pi. So the first thing I'm going to do, so for B, the first answer is going to be pi over 6 plus something, okay? Now that something is going to be the period of the function. So remember, when we talked about periodic functions, is that their values repeat over a certain period. So the function that we're looking at in this problem is sine x. So if you guys remember, when we graphed our trig functions, we found out that the period of a sine function, all right, was 2 pi. That meant that every time we went around this unit circle, a full rotation, we were going to go back to these original values. So every time, if I'm looking at my original answer here, pi over 6, every time I travel 2 pi worth around the unit circle, I'm going to come back to this same position that has a sine value of 1/2. So I'm going to take pi over 6, and I'm going to add 2 pi n to it, okay? 2 pi n, okay? The n just stands for any number that I want. It will constitute how many rotations I make around the unit circle. Every time I move positively around the unit circle, I can replace n with a positive value. Every time I move backwards around the unit circle, I can let n be a negative number. But this expression will give me all of the solutions for this particular problem, okay? I'm going to do the same thing with 5 pi over 6. So I have 5 pi over 6 plus 2 pi n, okay? So those two expressions will give me all of the solutions for this problem. So that's the answer for B. Awesome.